always have uncertainties. For example, when we measure the thickness of a book, we may obtain the thickness equal to 32 millimeter. Since the smallest scale of a ruler is 1 millimeter, we are not sure about the last digit. For example, the true value might be 31.3 millimeter or 32.6 millimeter. We often indicate the accuracy of a measured value by writing the number plus a symbol plus minus sign and a second number that shows the uncertainty of the measurement. In our case, for example, I can write the thickness equal to 32 plus minus 1 millimeter. In many cases, the uncertainty of a number is not given explicitly. In such cases, we can find an uncertainty by the number of meaningful or significant figures. As an example, consider these two numbers, 1.34 and 0.056. The first one has 3 significant digits, and the second one has only 2 significant digits. In the previous lectures, I have explained the scientific notation and also the significant digits. In such cases, when we deal with scientific notation or when the uncertainty of a measurement is not given, we can find the uncertainty by the number of meaningful digits, as I said. For example, if we are told that the thickness of a book is 2.91 millimeter, we see that this has only 3 significant digits. In this case, the last digit on the right is uncertain. Let me show it by a different color. The last digit on the right is not certain. In this example, the accuracy is 0.01 millimeter. In other words, I can write the thickness as 2.91 plus minus 0.01 millimeter. Now, what should we do when we want to multiply, divide, add, or subtract 2 or more numbers with different accuracies? We have a rule for this. When we want to divide or multiply 2 numbers with different significant digits, the result have no more significant figures than the factor with the fewest significant figures. Let me repeat it once again. When numbers are divided or subtracted, the result have no more significant figures than the factor with the fewest significant figures. Let me clarify this by 2 examples. The first example is this. I want to multiply these numbers, 3.1416 is multiplied by 2.34 times 0.58. I see that the first one has 5 significant digits. The second one has 3 significant digits, and the last one has only 2 significant digits. So the result is accurate only until 2 significant digits. So I should write the result as this, which has only 2 significant digits. So when you calculate this product by a calculator, you will see more digits, but you should ignore all of them because they are not certain. The next example, I have 0.745 times 2.2 divided by 3.885. Again, I see that this has 3 significant digits, this has 2 significant digits, and the denominator has 4 significant digits. So the result must be accurate no more than 2 significant digits, because the least accurate factor in this product has only 2 significant digits. So I should write the result as 0.42. Now when we want to add or subtract numbers, it's the location of the decimal point that matters, not the number of significant digits. In other words, the number of significant figures is determined by the term with the largest uncertainty. Let me clarify this by one example. I want to add 1 to 3.62 plus 8.9. The first number has 5 significant figures, and the second one has 2 significant figures. But the result is 132.5. This has 4 significant figures. So as you see in this example, the second factor has an accuracy equal to 0.1, and the first one has an accuracy equal to 0.01. So the accuracy of the product or the result must be equal to the accuracy of the factor with the least accuracy. In this example is 0.1. So this is also accurate until 0.01. Sometimes we deal with very large or very small numbers. In such cases, we use the scientific notation as I explained in my previous lectures. But the rules I mentioned for uncertainties is still valid. For example, consider this product. 9.11 times 10 to the power of minus 31 times 2.9979 times 8 times 10 to the power of 8, the whole to the power of 2. Let me first simplify the powers of 10. So I have 10 to the power of minus 31. Then I have 10 to the power of 8 to the power of 2, which is 10 to the power of 16. The result of this is 10 to the power of minus 14 times 2.9979. So when I use the calculator, I obtain this 8.1876 times 10 to the power of minus 14. But this is not true, because the factor with least accuracy in this example has only 3 significant digits. So the product should be accurate until 3 significant digits. But I have 2 options. I can write 8.18 times 10 to the power of minus 14, or 8.19 times 10 to the power of minus 14. Which one do you think is correct? In fact, in the last row, I have rounded. So as you see, this digit is 7, which is greater than 5. So when I want to write the final result, I should pay attention to this and round the last digit to the so I should round the last digit and write 8.19 times 10 to the power of minus 14 instead of 8.18 times 10 to the power of minus 14. So let me write it here explicitly. When we have a product we can round the last digit.